This lecture is about inductive proofs. And we are going to learn two techniques called structural induction and rule induction. First, we needed to learn why we need these two techniques, or why we need this notion called inductive proofs. So the story goes like this. We have this inductive system, like a syntactic category or system of judgment. Now, after giving this inductive definition, we'd like to prove some interesting properties. So we'd like to prove properties. So here's an example. Previously, we had this syntactic category called m-parent, which we defined in the previous lecture. So this syntactic category m-parent is intended to represent the strings of matched parentheses. But there's no formal proof. The definition, although the definition looks like correct, it does not automatically prove that any string that belongs to this m-parent indeed represent strings of matched parentheses. You have to prove this property manually, separately. So we wanted to prove, for example, every string that belongs to m-parent is indeed a string of matched parentheses. You want to prove this property yourself. So the reason that we needed these two techniques, like a structural induction or rule induction, is we'd like to be able to prove interesting properties of the inductive system that we define. So that's the reason. So after proving this property, then we convince ourselves that this definition indeed complies with the intuition that we had. So that's the reason. And there's another very important reason why we need this notion of inductive proofs and these techniques, structural induction and rule induction. It turns out that oftentimes this system, inductive system, can be very complex. It's so complex that its soundness may not be obvious. And what I mean by soundness is, informally speaking, you can think of a soundness as the system makes sense, or it has no bug or no error in the definition. But if the system is huge, very complex, then this soundness property may not be obvious at all. You have to give a separate proof of this property soundness. So here's an example. Suppose that we have a programming language. So this is a complete specification of a programming language. In functional programming language like OCaml, we have a soundness property called type preservation. So what this property means is that if you start with an expression of a type, say int, then after running this program, after evaluating this expression, you should end up with a value of the same type. So the type is preserved after this evaluation. So this is one of the soundness properties of this programming language. And we'd like to prove this soundness property, but it may not be obvious unless the system is that simple. If this type preservation does not hold, then you might be very surprised. For example, you started with a program of a type int, but later you end up with a value of a type bool, for example, which is very surprising. So depending on the complexity of this definition, this type preservation may not be easy to prove at all. So now why do we need to prove this soundness? Depending on the complexity of this system, it may have a bug or some error in this definition. And by trying to prove a soundness property, you might be able to find this bug, this error in this definition. Because if the system has a bug indeed, then you will not be able to prove this soundness property. So for example, suppose that this specification of programming language has some serious bug. Then when you try to prove this type preservation property, your attempt to prove this property should fail because there is a bug. So in the course of trying to prove this property, the bug manifests itself. You will be able to locate the bug in the definition. So the story goes like this. You have an inductive system, and the system is not trivial, and you are not sure if the system is okay. You are not sure if the system is sound or correct or makes sense. So what you do is you formulate some soundness property, say some soundness property, and then try to prove this property. And we can have two outcomes. First, there is a serious bug in this system, and there's no way to complete the proof of this soundness property. In that case, your proof will get stuck at some point, simply because there is a bug. And by analyzing why your proof cannot be completed, you can locate the bug. So you go back to the system and then fix the bug. That's one outcome. And the other possibility is the system is indeed okay. The system is sound. So you make it. You complete the proof. So here is the proof of the soundness property. What this means is that now you have higher confidence in the correctness of the system. The proof of this single soundness property does not guarantee that the system is perfect. It's just partial evidence that the system is working fine. But nevertheless, it's going to be very useful because by trying to prove several soundness properties, you can gradually increase your confidence into the correctness of the system. And in order to prove this soundness property, you need these techniques, inductive proofs, like structural induction or rule induction. I'd like to compare the story to debugging a computer program because you are computer science students. Suppose that you write a computer program. Unless the program is that simple, like just a few lines of code, you cannot convince yourselves that the program is working fine. So what you do is you try to prove a small soundness property. So for example, the program, when given an input of 0, the program is supposed to return an answer 1. You try to show that the program indeed returns 1 given input 0. If you fail to show this property, so for example, by manually simulating the execution or by compiling the program and then executing on a machine, you find that this property does not hold. It can be compared to the situation that the proof of this soundness property failed. Then it's good evidence that your program has a bug. So you analyze why this program doesn't work for this particular input, and you analyze the trace, and then you go back to the program and fix the bug. So you fix the bug. And then you can test more input cases. And as your program passes more test cases, you have better chance of passing all the tests. But still, it's just the partial evidence. Later, you might be surprised at the test result. But still, this is a very good way of finding bugs in your program. And this can be compared to this situation. You give this inductive system, and you are not sure whether the system is okay. So you try to prove this soundness property. And if the system has a bug, you might be lucky to find the bug because the proof does not complete. Or if the soundness property is shown to be true, then you have some partial evidence that the system is correct. So in conclusion, we need this notion of inductive proofs and this technique, structural induction and rule induction, in order to prove properties of this system or find the bugs in the definition.